Hi, everybody. In this lesson, we're going to look at independent events, and it's going to rely on our knowledge of those conditional probabilities. So an independent event we'll define shortly, but that's what this lesson and the next one are all about. So a hypothetical two-way table was constructed from the results of the 2016 presidential election based on gender and preferred candidate. So I have who they voted for, Republican, Democrat, or other, and then I have my male and female, and then I have the numbers and the totals according to that. So compute and interpret the following probabilities. So the first thing I want to do here is find P of R. What is the probability of me randomly selecting a Republican? Well, how many Republicans are there? There was 461 out of 1,000. I'm just picking someone at random. There's 461 Republicans in total out of 1,000, so that's 46.1%. What's the probability of me picking a Republican and a male? So this is an and probability, and we struggled with these last week. And probabilities come from the table, but it's out of the total still. So I'm still picking out of the 1,000 people. What's the probability I pick someone and they're a male and a Republican? So Republican and male, there's 244 male Republicans out of 1,000. So those make up 24.4% of our voters here. This next one is a conditional probability. Remember, this vertical bar here represents a given. I'm giving you information about the people you're picking. Find the probability of picking a Republican given you're only picking from the males. I shrunk your universe to only pick from the male voters. So I got rid of all the females, and I'm just looking at the males now, and I want to know what's the probability I'd find a Republican voter out of that. So my denominator became 470 because that's my total number of males. My universe shrunk to my given. Now, how many of those males are also Republican? Well, 244 of them. 244 of the males are Republican, which if I type into a calculator, I get about 51.9%. On web work, don't write percentages. Leave them as the fractions. Leave them as the ratios. Do not type in percentages into web work unless I explicitly ask for that. So that was a conditional probability. 52% of the male voters voted for the Republican candidate. 52% of the male voters, if I was just looking at males, 52% of them voted for the Republican. So based on the probabilities you calculated above, is there an association between gender and preferred candidate? Well, let's look at this. 46.1% of everyone voted for the Republican candidate. But if I just look at males, if we just look at males, 52% about voted for the Republican candidate. So knowing I was picking from just the males greatly increased the probability of me picking a Republican voter. So there is an association. There is an association. Males are more likely to vote for Republicans than just picking someone at random. Knowing I'm picking a male increases the probability of me picking someone who's going to vote for the Republican candidate. So we say two events are independent. We say two events are independent if knowing one event occurred does not change the probability of the second one occurring. So knowing that extra information does not change the probability. So let's answer this question. Are the events is male and prefer the Republican candidate independent? Well, look what we just said. Knowing a voter was male, increased the probability of picking a Republican voter. Knowing a voter was male increased the probability of picking a Republican voter. So we compare two probabilities, the probability of R and the probability of R given M. So the probability of R did not equal the probability of R given M. Notice the R is in the front seat of the condition. That's your repeated event there. The condition is not the same. That's when I'm going to pick a different event. So I find the probability of Republican, that was 46.1%, 0.461. And then I find the probability of picking a Republican still. So I'm still finding the probability of a Republican, but this time I gave myself a condition. I gave myself a condition that I was only picking from the male voters. And that greatly increased the probability. Those two probabilities are not equal. Since they're not equal, they are not independent. These events are not independent. You have independent events if they're equal. If knowing that extra information didn't change the probability, but knowing that extra information of picking a male voter changed the probability of me finding a Republican. So let me say this again. For two events to be independent, it means the probability of the event occurring is the same as the probability of that event occurring given B. So knowing that extra information doesn't affect the probability of A occurring. The conditional probability is the same as the plain old probability of A. So the P of A has to equal P of A given B. So using that condition doesn't change the probability. So let's practice this. A survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. So we've got their favorite subject, and we've got female and male. Based on this table, is preferring math independent of the student's gender? So let's find the probability that someone likes math. I'm just picking that. Probability of math. How many people like math? 18 out of 57. 18 people out of 57 is approximately, if I hit enter here, 31.6%, 0.316. Now to test for independence, I find the probability of math again. I'm still finding the probability of math, but let's say this time given female. So I'm only looking at the female row. I'm only allowed to pick from the female students. From them, what's the probability that someone likes math? Well, 8, be nice if I went back to a pen, 8 out of 30. I found a conditional probability there. Math given female. 8 out of 30 comes out to be 0.267. So are these events independent? Knowing I was picking a female decreased the probability of me finding someone who liked math. So these events are not independent. These are not independent events. These are not independent events because why? Porque why? Because the probability of A does not equal the probability of A given the other event occurred. So math goes in the front seat both times, but this time I had to condition it with given the female piece. So they are not independent because these two probabilities are not equal. So when we test for independence, we find a probability, and then we find that same probability with a condition and see if that changes the probability of the event occurring. So based on this data table, is preferring social studies independent of gender? So let's find the probability of social studies. How many kids like social studies? Well, 19 kids like social studies out of 57. 19 out of 57. If I type that into my calculator over here, I get a third, 0.333 repeating. Now, let's compare that with social studies again, the probability of social studies given the student's gender. Let's use female again. So I shrunk my universe. I'm only allowed to pick from that female row. My denominator is 30. 10 like social studies. So 10 out of 30 is also a third. That's 0.3 repeating. So look at this. Knowing I was picking from a female, did that change my probability? No, it's basically the same. So I'm going to say social studies and gender are independent. Doesn't matter if you're male or female, you're just as likely to pick social studies as your favorite subject. Social studies and gender are independent events. Because why? Because the probability of social studies equals the probability of liking social studies given that you're a female. These two probabilities are equal. I compare the plain old probability with that same probability, but this time given some extra condition. That's how we test for independence. We find two probabilities and we compare to see if they're equal. We got Titanic here. I have some music to go along with this problem here. So we can't do a Titanic problem without a little My Heart Will Go On. So on April 15th, 1912, the Titanic struck an iceberg, so sad and rapidly sunk, with only 710 of her passengers and crew surviving. Some believe that the rescue efforts favored the wealthier first class. Data on the survival of passengers are summarized in the table below. Yes, this is the bad recorder version, which is a classic My Heart Will Go On cover. We'll just let it play for a second. I hope this brings you back to your third grade recorder days. Alright, we'll stop. We'll stop that right now. Nope, I want it to stop. It won't stop. There we go. Come on, YouTube. I'll just have to X out. There we go. All right, it's gone. Maybe I'll sing My Heart Will Go On later in this video. Do these data suggest that a passenger's class and survival status are independent of each other? So if I want to test for independence, I find two probabilities, and you have some freedom here. Let's look at the probability that someone survived. What's the probability that I survived? How many people survived? Of the passengers, 500 passengers out of the 1317 passengers survived. And yes, guys, this is real data. I wouldn't lie to you with fake data here. So I got 0.3797. So about 38% of the passengers survived. Overall, on the boat, 38% of the passengers survived. And now I'm going to compare that with something. I'm still going to find the probability that someone survived. But this time I'm going to add in a condition. I'm going to condition it on them being first class. So I'm still finding the probability that they survived, but this time I conditioned it on I'm only allowed to pick from my first class passengers. So of my first class passengers, of those 324 people, what proportion of them survived? 201 survived out of that. And if I find that ratio, 201 divided by 324, ouch, 62.04. So let's look at this. If you just pick someone randomly from the Titanic, a random passenger, there's about a 38% chance they survived. If you pick from just the first class people, 62% of the first class people survived. Clearly, these events are not independent. Clearly, surviving and what are we calling it? Passengers class are not independent. Being in the first class greatly increased the probability of survival. Being a first class passenger greatly increased the probability of surviving, which makes sense. The first class passengers are the wealthy people on the boat who paid good money. You could have also used other probabilities here. This isn't the only way to do this problem. You could have used lots of different probabilities and you would have ended up with the same result, that there's some imbalance here, there's some inequity, which means that they are not independent. Independent would mean, doesn't matter if you're first class, second, or third class, there's a 38% chance you survive. But that's not the case. 62% of my first class passengers survived, whereas overall on the whole boat, only 38% of people survived. So we got one more problem for this lesson. We're going to skip 5 and jump to number 6, and then we'll call it an independent event lesson, even though the next video is going to be all about independent events round 2. So today there's a 55% chance of rain. When I'm making this video, it's actually a 100% chance, but that's okay. There's a 55% chance of rain, a 20% chance of lightning, and a 15% chance of both. So the probability it rains is 0.55. The probability of lightning is 0.20, and the probability of rain and lightning is 0.15. Are these events independent? That's my question. Is rain and lightning, are those independent events? Does knowing it's raining affect the probability of lightning? Or does knowing it's lightning affect the probability of raining? So the way that we do this is we find a conditional probability. Let's do P of R given L. So what does this mean? This means we know there's lightning. We know there's lightning already happening. What's the chance of it raining? Well, we know there's lightning happening, so that's your denominator. 20% goes in the denominator. What goes up top? Well, we know there's lightning, so I can't use this 55%. I have to use the and probability, because in lesson 3, I define the probability of A given B as the probability of both of them occurring, A and B, divided by the probability of your given divided by B. So I defined a conditional probability last lesson as the probability of and over the given. So that's what I used here. The probability of both of them, the and probability, both occurring over the lightning. 15 over 20 is 75%. So what do I compare that with? Well, I use P of R given L. So what's the P of R? Well, it's only 55% chance. So are these events independent? Are those two probabilities there equal? No, these events are not independent. These events are not independent. They're not independent because knowing there's lightning increases the chance of there being rain. Knowing there's lightning occurring increase the chance of rain from 55 to 75. No, these events are not independent because P of R does not equal P of R given L. So that's how we test for independence. Is my conditional probability the same as the plain old probability? Did knowing that extra condition change the probability of that event occurring? I'll see you guys in the next video with less Titanic music and less My Heart Will Go On.